All right, let's get right into it. We're talking about something that is, without a doubt, one of the most critical, high-stakes measurements in any pharmaceutical facility, the conductivity of your purified water. If you get this right, you're golden. But if you get it wrong, oh, the consequences can be absolutely massive. So today, we're going to break down the science, the regulations, and the engineering playbook you absolutely need to master this. And believe me, that is no exaggeration. We are talking about a single tenth of a microsiemen. That tiny, tiny fluctuation can be the difference between a totally smooth operation and a complete shutdown. The stakes have just never been higher, especially right now, with regulators watching more closely than ever before. So, let's talk about the core challenge here, what I like to call the 1.3 microsiemen problem. Now, this isn't just some number on a screen. It's the finish line in a race that you are running 24/7. For years, the whole industry has battled to stay below this limit. But the nature of that battle, well, it's changing, and it's changing dramatically. Now, what's so interesting here is how the threat itself has evolved. You see, it used to be pretty simple. Did you go over the limit? Yes or no? Easy. But today, the FDA isn't just looking for those obvious spikes. They're hunting for suspicious trends, for patterns hiding inside your data. And they are deploying some seriously powerful new AI to do it, which, let me tell you, changes everything. So meet Elsa. This is the FDA's new AI Auditor, and it is a complete game changer. It can sift through years of your water system data in seconds, flagging these subtle shifts and tiny anomalies that a human inspector might easily miss. If your data tells a story of instability, Elsa is going to find it, and you will have to answer for it. Okay, so to survive in this new era of intense scrutiny, we have to go back to the source code of compliance itself, USP General Chapter 645. Think of this as the official rulebook, and understanding its nuances is your absolute first line of defense. So why do we even measure conductivity in the first place? Well, it's pretty simple, really. It's the fastest, most direct way to measure the total amount of dissolved ionic impurities in your water. See, pure water is a terrible conductor of electricity, but impure water is a great one. For our purposes, stage 1 of the USP test is the holy grail. It's that real-time online measurement that proves your system is in a constant state of control. And there it is, the magic number, 1.3 microsiemens per centimeter, at a temperature-compensated 25 degrees Celsius. This is the absolute, non-negotiable ceiling. If you cross this line, it's an undeniable failure. But, and this is the crucial part, just staying under it is no longer good enough. This right here is the new paradigm. The FDA, powered by tools like Elsa, is now totally focused on data trends. A system that's consistently stable at, say, 0.7 microsiemens is seen as way more reliable than a system that swings wildly between 0.9 and 1.2, even if it never actually breaks that 1.3 limit. You see, stability is the new compliance. So let's look at how this actually plays out inside your facility. Your alert limit, maybe you set it around 0.8 or 1.0. That's your early warning system. Your action limit, say 1.1 or 1.2. That means you have a formal deviation. You have to launch an investigation, do a full root cause analysis, get a CAPA plan going. But the real FDA red flag, it's that sudden jump. If your system runs at 0.6 for 6 months straight and then suddenly shifts to a new stable point of 0.9, the auditor's question won't be, is it compliant? It's going to be, what changed in your system and why? Okay, enough about the problem. Let's talk solutions. Because when that alert limit starts flashing, you need a plan. This isn't some ghost in the machine, it's an engineering problem with a real physical cause. So here is your rapid response checklist. These are what I call the 4 horsemen of high conductivity. First up, carbon dioxide. It is the #1 silent killer. It sneaks in through a bad vent filter, forms carbonic acid, and sends your conductivity readings soaring. Second, your RO membranes. Seasonal changes in your feed water can totally overwhelm them. Third, your EDI unit. If that DC voltage is off or the resin beds are fouled, it can't polish the water and ions will just slip right through. And finally, the simplest one of all, your sensor. A bad temperature compensation reading can throw everything off. Now, that checklist, that's for emergencies. For long-term mastery, what you really need is a proactive strategy. And that strategy should be built on these 3 engineering pillars. This is how you move from just reacting to problems to preventing them from ever happening in the first place. So let's break these down. Pillar number 1 is an aggressive degassing strategy. Don't wait around for CO2 to get into your storage tank. The absolute most effective approach is to remove it right after your RO unit, using something like a membrane or a forced draft degasser. This one step can often keep your conductivity consistently below zero point 0.5 microsiemens. That's what I call proactive control. Next up, your sensors. These are your eyes on the system, and they cannot lie. A monthly verification with a certified external meter, that's completely non-negotiable. But what's even more critical is the quarterly physical inspection. Why? Because biofilm or mineral scaling on an electrode can actually insulate it, causing a falsely low reading. Think about that. That is a catastrophic data integrity failure just waiting to happen. It's telling you everything is fine, when in reality, your water purity could be totally failing. And pillar number 3, move that water. Stagnant water is the enemy. It allows ions to leach out from the piping, and even worse, it creates these little breeding grounds for microbes. By maintaining a turbulent flow, and we're generally talking above 1.5 meters per second, you keep the whole system continuously flushed, preventing any of those pockets of contamination from ever forming. So, you've put in the engineering fixes. Your system is stable. Now what? How do you prepare for this new reality? How do you actually prove your state of control to an AI auditor like Elsa? This right here, these are the new rules of engagement. You have to become the absolute master of your own data story. Document everything. When a trend shifts, you need a corresponding entry in your logbook, something like performed RO membrane sanitization or replaced EDI unit. You have to secure your data logs so they are unalterable. And you have to know your system's history better than anyone, so when that AI flags a change from 2 years ago, you have the answer ready to go. You know, at the end of the day, all of this, the limits, the engineering, the data integrity, it all comes back to one thing, and one thing only: the patient. We just can't lose sight of the ultimate mission here. And this is the bottom line. It's the fundamental truth of pharmaceutical manufacturing. The water you use is a primary ingredient, and its purity directly impacts the safety and the efficacy of the final product that reaches a patient. There are absolutely no shortcuts. So how does this actually work on a chemical level? Well, excess ions aren't just an impurity, they're catalysts. They can actively degrade the drug itself, reducing its potency. And what's worse, impure water can be aggressive, literally leaching metals and other contaminants from your piping directly into that final product. So as we wrap this up, I want to leave you with a question to really think about. It doesn't matter if you're in quality assurance, engineering, or production. What is that one trend, that one logbook entry, that one piece of your water system's story that you dread having to explain to an auditor? See, mastering your system means having an answer for that question before it's ever even asked.